On this computer. Okay, so if our function is above the x-axis, our integral should always come out to be positive. If our function is below the x-axis, our integral should, we'll call this g of x. Our integral should always be negative, meaning that if we're looking for the area for a curve, the area between a curve and the x-axis, if it crosses through the x-axis, we've got to split it there and take the opposite of any integrals that are below the x-axis. Everybody good with that, I hope. Anytime we're looking just for the value of the integral, it doesn't really matter. If we have two different functions, let's say f of x and g of x, and we're looking for the area between the two of them, let's say from a to b, all we have to do is the integral from a to b of f minus g. And so all we have to do is just take the upper one, subtract the lower one. In this case, if we're looking for the area between them, it doesn't matter if one of them lies partially below the x-axis or if one of them lies entirely below the x-axis, or if both of them are entirely below the x-axis. The subtraction between the two functions takes care of any negative values underneath that integral. So all you have to do to find the area between the curves is just subtract the two functions. Everybody good there? Easy enough, I hope. Oh, and people are entering the room. Okay. I'm not going to go through all of the basic rules for integrals because we should know all of the basic rules for our integrals. But we should talk about what happens. Let's see. Let's talk about some of the new stuff we did with integrals. So let's talk about integration by parts first. Our integration by parts formula should be the integral of u dv is equal to u times v minus the integral of v du. So if we're given if we're given some function like, I don't know, what's a good function we should use for this? How about, let's just integrate x e to the x. If we want to integrate x e to the x dx, what should we do with that? What's the first thing we should do? What should be u and what should be dv? Let u equal x, and we should let dv equal e to the x dx, and then we can say that du is just equal to dx, and that v should be the integral of this, which is just e to the x. And then we just straight through go and write out the formula here. The integral of u dv should be equal to u times v, so x e to the x, minus the integral of e to the x dx. And so that should give us x e to the x minus the integral of e to the x, which is e to the x, plus our constant. So just a basic example for this. We hopefully remember that sometimes what happens when we're doing these integration by parts is we'll end up with the same integral that we were originally looking for within this integral within the integration by parts. And in that case, we have to gather all of those terms to the other side with our original integral. So I think this is one that ought to work. Let's suppose we did something like e to the x sine x. So here, if we let, let's say we let, doesn't really matter, let's let u equal sine x and dv equal e to the x. Du will be cosine x and v, cosine x, dx, and v will be e to the x. I should put my dx up there too. So this is the integral of, this is our integral of v to u, so it should become u times v. So it should become e to the x sine x minus the integral of v du, which is e to the x cosine x dx. And from there, I would do this in a different color if my toolbar was showing up, but I guess it's not. We're going to do another integration by parts for the e to the x cosine x. I'm probably doing the same thing. I'm just going to let u equal cosine. And so du will be negative sine x dx. Our dv will be e to the x dx, and our v will just be e to the x. And so this should become e to the x sine x minus, and then we've got u times v now, which is e to the x cosine x, and then minus the integral of v du, which that's a negative sine x e to the x, but I can make that a plus e to the x sine x dx. And we'll note that at this point, we've got this integral, which is the same as this integral that we were originally looking for. And so we'll go back over here and say, well, we were looking for this integral, e to the x sine x dx. We'll set this whole thing equal to it. And then we will, since this becomes a minus e to the x sine x, we'll bring that over to the other side and make this 2 integrals of e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x plus our constant. And then we just divide everything by 2. Get rid of that 2. Well, remember that. Seems vaguely familiar, hopefully. Any issues there with that? Re-explain that from the last part. What do you mean? Just right down here where I had this, and then how I got to the end. Yeah. Okay. So I have this, right? And we note that the integral that I was originally looking for, the integral of e to the x sine x dx, shows up within the integration by parts formula here. And so if we distribute the minus sign of e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x, so we just add that negative integral of e to the x sine x as a positive over here to make it 2 integrals of e to the x sine x. And so we have 2 integrals of e to the x sine x dx equals e to the x sine x minus e to the x cosine x plus our constant. And then we just divide by 2 to say the integral of e to the x sine x is this thing that we had divided by 2. Does that make sense or no? Cool. All right, so that's the basic idea for integration by parts. Just a few things to remember with it. Usually you want to make your dv the whatever term you can easily integrate, like the more complicated term that you can just easily integrate is a good choice for your dv value. Should also remember that there is this idea of tabular integration, right, where we have something like an integral of x squared e to the x dx, just a simple one here. And we know that one of the 2 pieces of this, in fact, this piece of it, differentiates down to 0. If I were to repeatedly differentiate it, you can just do the integration by parts in a shorthand called tabular integration. So take the derivative of the x squared as 2x, take the derivative of 2x as 2, and take the derivative of the 2 as 0. And then from there, you take the integrals of e to the x. And in fact, let's make this, just so that the integrals are all different, let's make that e to the 2x. So the integral of e to the 2x ought to be 1/2 e to the 2x, and the integral of that ought to be 1/4 e to the 2x, and the integral of that ought to be 1/8 e to the 2x. And so then you just take the first term up here, what would have been your u, and you put it with your, what would be a v, because this is dv, so the integral of the dv would be v. So you put those 2 together, x squared and 1/2 e to the 2x to get 1/2 x squared e to the 2x. And then we take the next 2 terms and we subtract. So minus and then it becomes x over 2 e to the 2x. And then we take the next two terms and add them, so plus just e to the 2x over 4. And then we're at the end, we get to the 0, so we're done, plus a c. And so this is tabular integration. It's just a shorthand for your integration by parts whenever you have a term that can differentiate down to 0, as long as you can continually integrate the other part of it. Good or no? Hopefully good. All right. Let's see here. Suppose we had a integral like this one. This one does not have an easy, simple U substitution. It's just a rational function. And if we have a rational function that we don't see an easy U substitution, or it isn't just a specific integral that we should know and have memorized, normally what we need to do is the partial fraction decomposition so that we can put it into a nice, easy form for us to evaluate. So first thing you have to do is factor your denominator, x minus 3x plus 2. And then we'll write it out off to the side as, we'll say 3x plus 11 over x minus 3 times x plus 2 is equal to, we'll say, capital A over x minus 3 plus capital B over x plus 2. Okay. And these are distinct linear factors. If you have distinct linear factors in the denominator, you just put a constant in the numerator. If this was an x squared minus 3, though, you would make this an ax plus b up there. So if you have a irreducible quadratic factor, you put a linear factor in the top. If you have an irreducible cubic in the denominator, you'd have to put a quadratic in the top. And so on, just 1 degree less the entire time. Good or no? And then we cancel out all the denominators by multiplying the a by x plus 2 to get the common denominator, and the b by x minus 3. So this becomes a times x plus 2, or ax plus 2a, and then b times x minus 3, which is plus bx minus 3b. And then we just use a system of equations. We say we have 3 x's on this side. So 3 needs to equal the number of x's over here, a plus b. And here we have a constant of 11. 11 needs to equal the constant on the other side, which is 2a minus 3b. And then we just solve this system of equations. So we can multiply this top one by 2. And if we subtract, we end up with 5 equals negative 5b. So b is equal to negative 1. And if b is equal to negative 1, then that ought to give us a is equal to 4. Everybody good there? And so we end up with an integral of 4 over x minus 3 minus 1 over x plus 2 dx. And we should be able to easily integrate that. 4 natural log absolute value x minus 3 minus natural log absolute value x plus 2 plus our constant. Good or no? Okay. Now I doubt that they will give you anything more than a linear, irreducible linear piece. They might give you an irreducible quadratic. So if we had something like, we wanted to find the integral of, I'm not going to do this full integral, but if we wanted to find the integral of like 2x plus 7 over x cubed plus 4x squared, we'd factor out that bottom. Oh, sorry, not x cubed plus 4x squared, just x cubed plus 4x. We factor out that bottom to x times x squared plus 4. And so our partial fraction decomposition would look something like 2x plus 7 over x times x squared plus 4 equals a over x plus bx plus c over x squared plus 4. Right? Because this is an irreducible quadratic factor, so it has to have a linear piece in the numerator. Everybody good with that? Okay. And if we had something like the, let's say the integral of let's say x over x cubed minus 4x squared plus 4x. As we were to go through and factor this out, we'd end up with the integral of x over x times x squared minus 4x plus 4, which would be x minus 2 squared. And so this time we have a repeated linear factor. And so when we were to write out the partial fraction decomposition for this, it'd look like x over, let's call this like x plus 1, just so we don't have to turn the cancels there. So we have x plus 1 over x times our x minus 2 squared should equal a over x plus b over x minus 2 plus c over x minus 2 squared. Right? And if this was x minus 2 to the third, I'd have a d over x minus 2 to the third, and so on. Same thing would happen if like this was an x squared plus 4 squared. Well, I'd have bx plus c over x squared plus 4, and then I'd have dx plus e over x squared plus 4 for the second one. So anytime you have repeated irreducible factors, you just have to put a term for each power of it. Good or no? Irreducible, when I say irreducible, I mean like can't factor it any further. So like x squared plus 4 has a factor on the real number system, so we can't reduce it, or it doesn't reduce using whole numbers. Yeah, no problem. Why do I need the b over x minus 2? So for every instance, in every instance of the linear factor that gets repeated, I have to have a constant over the linear factor itself, and then a new constant over that linear factor to each power that it might have. So if I was x minus 2 to the fourth, I'd have 1 for x minus 2, 1 for x minus 2 squared, 1 for x minus 2 cubed, and then 1 for x minus 2 to the fourth. You just have 1 for each different instance of it. Everybody good there? And a couple of things to remember when you're doing partial fraction decomposition integrals. First off, that if the degree of the numerator is greater than or equal to the degree of the denominator, you want to do long division first, right? So if I had, suppose we had, let's put it here, I don't know if this will come out nicely, but suppose we had something like x to the fourth plus 1 over x cubed minus let's say. If we wanted to integrate that, the first thing we do, since the degree is greater than the degree of the denominator, the degree of the numerator is greater than the degree of the denominator, we just do long division. And remember, if you're doing your long division, don't forget to put in all of the missing terms. X to the third goes into x to the fourth x times. We'd have x to the fourth, and then we'd have minus x squared here. When we subtract, we'd end up with a positive x squared plus a 1 down here. And we'd see that we are then, we're now out of, we can't do x cubed into that anymore. So this integral would become the integral of x plus x squared plus 1 over x cubed x dx. Then you can integrate the first piece really easily, and then the second piece you'd have to use partial fraction decomposition to integrate it. Good or no? So remember always to do that partial fraction decomposition. If the degree of the numerator is greater than or equal to the degree of the denominator. All right. Important integral that you should remember that sometimes shows up in these partial fraction ones is 1 over x squared plus some constant squared, 1 over x squared plus a squared. That integral is always equal to 1 over a inverse tangent of x over a plus your constant. So this is a good one that we need to know. Let's see. What else? Anything else with partial fractions? We should talk about the real quickly. We had the integral of what was it? 1 over x squared minus a squared. This one we talked about. And the integral of 1 over x squared minus a squared. This is another one you should have memorized. 1 over 2a times the natural log of the absolute value of x minus a over x plus a plus a constant. That's another good one to know. So make sure you've got that one. I'll put that on the sheet also. But that's a good one. I don't know if we talked specifically about this one, but if you had 1 over a squared minus x squared, that integral is just 1 over 2a natural log absolute value of x, well, normally we write it this way, a plus x over a minus x. That might be a good one to know also. You can figure those ones out fairly easily though, just by doing the partial fraction decomposition. But if they show up, it's just helpful to know them. Feel like that's pretty good for partial fraction decomposition. Anybody have any questions on either partial fraction or any of the integration by parts stuff? All right. The trig substitution integrals. So the substitutions you should know is if you're ever looking at an integral that's got something of the term square root of a squared plus x squared in it. You're going to want to make a substitution where x is equal to a tangent theta, most likely. If you have something like the square root of a squared minus x squared, you're going to want to make a substitution where x is equal to a sine theta. And if you got something like the square root of x squared minus a squared, you're going to want to make a substitution where x is equal to a secant theta. Everybody good with that? We remember those? Should we do one of these here? Okay. So let's I don't know, let's see here. Let's see if I can come up with something that'll work out not so awfully. Let's try this. The square root of x squared plus 16. Let's just put that over x to the 4. I think that ought to not be too bad. There, looks like an x now. So this is one where we'll use a tangent substitution. The constant is 4 being squared here, so we'll just let x equal 4 tangent theta. Don't forget to figure out what dx is in terms of theta. It should be 4 secant squared theta d theta. Then we just go back in and we do all of this substitution. So this becomes an integral of the square root of 16 tangent squared theta plus 16 over 4 to the 4th tangent to the 4th of theta. And then we have a times a 4 secant squared theta d theta. And we should be able to do some simplification here. First off, the 16 plus the 16 here can factor out as just a 4 times this 4. So 16 over 4 to the 4th, which should give us a 16 in the denominator. So we can put that 1/16 out in front. And then when we did the factoring out of that 16, that left us with a tangent squared plus 1 inside of here, and 1 plus tangent squared is secant squared, and the square root of secant squared is secant cubed. Is secant times the secant squared gives us a secant cubed. So we end up with 1/16 of secant cubed theta over tangent to the 4th theta d theta. And simplifying that down, this is 1 over cosine cubed. This is sine to the 4th over cosine to the 4th. So we can get rid of a cosine cubed in the denominators of each of those. So really all we end up with here is sine to the 1 over sine to the 4th theta over cosine theta, which ought to just be 1/16 of cosine theta d theta over sine to the 4th theta. And from there, we'll just let u, this is just a simple u substitution now. We let u equal sine theta, du is cosine theta, d theta. And we've got 1/16 of the integral of u to the -4 du, which should become, go up to u to the -3, divide by the -3, it should be -1/48 of u to the -3, or -1/48 u cubed plus our constant. And then you just go substitute back in. So our u is sine, so we got sine cubed theta, but then we got to get all the way back into terms of x. And so in order to figure out our values there for what sine is, we need to go back and make a triangle here and say if x is 4 tangent theta, that means tangent theta, which is opposite over adjacent, should be x over 4. This last side using the Pythagorean theorem is x squared plus 16. And that gives us -1/48. And then it's a sine cubed. So we just look at what is sine. Sine should be x over root x squared plus 16. And so we'll just say x over root x squared plus 16 cubed plus our constant. And obviously we could flip this so that we had the x squared plus 16 would be to the 3/2 over x over 48x cubed would be fine if you want to simplify it down. But does that make sense? Anybody have questions on that? That's the basic process for those. I don't know who that is, but somebody has got themselves unmuted. Everyone good there with that? All right. Another good important thing we need to know with integrals is we need to be able to convert back and forth between from Newton's or into Newton's notation from Leibniz's notation. There's usually like one question in the multiple choice where they ask you to do that. So let's say we were looking at the integral of, I don't know, just something simple like x squared dx from 1 to 3. The important things to remember here for this is that this should always become the limit as n approaches infinity of the sum from k equals 1 to n of our, well, we'll say f of x sub k, so this is x sub k squared times delta x. It's always f of x sub k times delta x. And so then you need to just figure out what is delta x. Well, delta x is always equal to b minus a over n, which you should know. So that's 3 minus 1 over n, or 2 over n. And our x sub k is always equal to a plus k delta x when we're doing this using, it's easiest to do this using a right Riemann sum. That's what they always ask about. So our a value is 1. Our delta x value is 2 over n. So this is 1 plus 2k over n. And we end up rewriting this then as the limit as n approaches infinity of the sum from k equals 1 to n of x sub k, which was 1 plus 2k over n, squared times delta x, which is 2 over n. And generally, this is all they'll ask you to do with it. They won't ask you to finish evaluating and solving it all the way out using the summation. They don't ever ask you to do that. So everybody sort of remember how to do that. The important thing is if you can remember these, it should be really easy to put it into this form because this doesn't change. Whatever your function is, you just replace the x with x sub k, attach a delta x at the end of it, which is representative of your dx, and plug in the numbers and get your expression. Good or no? Yes, Nick, you're not going to have to evaluate. I mean, they might have you like distribute this out, but I have never seen a question where they actually make you evaluate it. That's just me that makes you guys evaluate it because I think it's important for you to know those summations for future math classes and stuff. All right. Let's see, you're still talking integrals here. Suppose we want the area of a polar curve. So the area of a polar curve should be 1/2 the integral from alpha to beta of your r function, r squared, d theta. So if I were to ask you, what's the area of, I don't know, the function r equals 1 minus sine theta, let's say from theta equals pi, and let's just start at 0. Theta equals 0 to pi over 6. Just make a nice little easy one here. this should just be set up as 1/2 the integral from 0 to pi over 6 of 1 minus sine theta squared d theta. And I've seen a lot of people lately, like on the area quiz and stuff, where they're not putting that 1/2 and not squaring that r value. You gotta do both those things, right? Because that we developed that formula by using the area of the sector of a circle, and so that's effectively what we're doing here. It should be, it comes out to be 1/2 r squared d theta. If we want to, we can write all of this out. Oftentimes these become a little bit irritating, but it's probably important for us to at least have a vague recollection of how to integrate sine squared. So this just becomes 1/2 of theta, and our integral of -2 sine theta ought to be positive 2 cosine theta. But to integrate sine squared theta, you've got to use the power reducing formula on that. Geez, now let's see, that should be 1/2 of. Now I'm forgetting if sine squared is the positive or the negative. It doesn't seem like I should be forgetting that. Should be the
negative.
Negative one. I believe. Yeah, there we go. 1 minus cosine 2 theta. That's what I thought. So 1/2 of 1 minus cosine 2 theta d theta, and then you should be able to integrate it from there if we're doing something. Remembering this is still from 0 to pi over 6. This will also get evaluated from 0 to pi over 6 eventually. And as we integrate this becomes a theta over 2. I'll get a page for this. Let's see. We got 1/2 of theta plus 2 cosine theta. And then we got a positive 1/2, so that becomes a plus theta over 2. And then we've got a minus 1/2 cosine 2 theta, which should become a minus 1/4 sine 2 theta. And then we can evaluate that from 0 to pi over 6. And I'm not going to bother to go through and evaluate, but it's conceptually okay there. Cool. If you are looking for the area between two polar curves, you've just got to figure out where they intersect and do the outer one minus the inner one. Just be careful with your limits. So like if I was looking at this polar curve and that was not what I wanted that to be. Let's do this. And this polar curve. And I wanted to know, let's say, this shaded region here. Make sure you start at this intersection point and go to this intersection point. Don't start here and go to here. That will give us the other area on the inside. Right? And oftentimes, like for example, for this one, let's suppose this was a circle and then this was just a cardioid here. If we're looking for the area that's inside the circle but outside of the cardioid, we could just find the area of this full semicircle here and then subtract off the area of the cardioid, which is just these two little slivers there. But sometimes if you're trying to find, like, let's say we were looking for the area that was both inside the cardioid and inside the circle, and that one's not too bad either, actually. We just take this semicircle and add the area from here to here of the cardioid. Yeah, actually, this one turns out to be pretty easy to find any of them. So just be careful with your where they hit, like where they intersect with each other, and make sure you're going in the right direction to find the piece that you are specifically looking for. Does that make sense to everybody? It's outside minus inside for the most part, as in like, yeah, I mean, yeah, generally so, yeah. But just don't forget the 1/2 r squared, right? Lots of people get them set up correctly with like the outer minus the inner and the right limits and all that, but then just do the integral of r, or sometimes the integral of just r squared and forget the 1/2. So don't forget either piece of that. What else? That's about it for polar integrals. You know, arc length formulas, I'm not going to go through and do a bunch of arc length formulas, but know the arc length formula. You know, for regular Cartesian equations, should just be the integral from a to b of the square root of 1 plus f prime of x squared dx. And if we're doing it for a parametric or for a polar, our integral should be just the integral from going back. There we go. All right, if we're doing it for a parametric, it should be like an integral from first t value to the second t value of the square root of dx dt squared plus dy dt squared. And if you were doing it for polar, it's just dy d theta squared, and or dx d theta squared and dy d theta squared inside of there, from your first to your second angle. So those should be pretty straightforward. Usually the arc length ones come up in a calculator question, but every once in a while they don't. You know, a lot of the arc length ones, just the numbers come out to be really annoying. So yes, you might see that in a calculator, but it's possible you might not even actually, not like it's difficult, but you might actually have to take the derivative and square it to get your integral to actually evaluate. Let's see, volume stuff. So if we're talking about volume stuff, we want to revolve around the x-axis or the y-axis or some horizontal or some vertical line. It should always just be an integral from a to b of pi times the radius squared, dx or dy, just depending on whether you're doing it in terms of x or in terms of y. I'll just write dx there. If we're revolving around, this is if we're doing disks. So if we're revolving around, you know, some function f of x, a to b, we're revolving it around the x-axis, and we're going to get these circular cross sections through each piece. And so the radius is just f of x. Whenever we're pushed up fully against the axis that we're revolving around, if it's the x-axis, our radius should just be the value of the function, and pi times the integral from a to b of that. If we are looking at a function that is not fully pushed up against the region, like we might have two different functions here, right? And we say we're going to go from a to b, we're going to take this section right here and revolve it around the x-axis. That's f and g. We've got to do pi times the outer radius squared minus pi times the inner radius squared to find that one. We can also go and do these in terms of y. We can do any of our integrals in terms of y. Just thinking back to if we need to just even find an area between a curve and the y-axis, or we can just find the area between two curves doing it in terms of y, or just of some random region. Like suppose we have some region, let's do it this way, this will be better. Some region like this, where it's like a logarithmic function and then a linear function here. So if we're looking for the area, let's say this area right here between those and the x-axis, let's suppose this is y equals negative x plus 7, and this is just ln x. To find this area, you can split it at this point, figure out where the intersection point is, and do an integral from 1, this would be 1 where they cross, to that intersection point of just ln x. And then you can add to that the integral from this intersection point to 7, where this crosses through the x-axis of negative x plus 7. Or you can integrate in terms of y. So we'll go from 0 to, we'll just call this x1, y1, so I don't have to actually solve it. So 0 to y1 of the rightmost function, negative x plus 7, minus the leftmost function, ln x. So if y is equal to negative x plus 7, that tells me that x is equal to 7 minus y, so it'd be 7 minus y. And if y is ln x, then x is e to the y, so it'd be 7 minus y minus e to the y dy. And we can get the area in terms of y that way, by integrating in terms of y. Everybody good there with integration in terms of y? Okay, and so if we wanted to take some region, I don't know, let's say yes, Nick, y1 was my value of my intersection point there, the y value of my intersection point. Let's suppose I had this. Let's just do the right-hand side of this parabola. Suppose we were taking this region right here and revolving it around the y-axis. We could do that in terms of y, because if we slice it horizontally like this, with a thickness of dy, we get disks, so it should be pi times the integral of this radius. So we have to figure out what this radius is from 0 to, and once again, I'm just going to call this y first, but y1. So 0 to y1. Whatever this radius is, well, this radius is just the whatever x value I've gone over. And so if this is y equals x squared, then x is equal to the square root of y. And so this would just be square root of y squared dy, or radius being square root of y squared, because it's pi times the radius squared, and you can find your volume that way also. Everybody good with that? Hopefully. All right. Can also revolve around lines that are not the x or the y-axis. So suppose I had some function up here and some other function here, which is called f and g, and I want to revolve them around the line y equals negative 1 from A to B. Our outer radius is 1 plus f of x. So this should be pi times the integral of 1 plus f squared minus 1 plus g squared dx. So you just find your outer and your inner radius. Outer radius squared minus inner radius squared times pi integrated from A to B. Good there or no? And we could do the same thing if it was a vertical line, same basic concept. What about our improper integrals? Everybody remember improper integrals? That wasn't actually all that long ago. So with our improper integrals, if we're looking for like the integral from 1 to infinity of something like 1 over x squared dx, we just need to rewrite this as the limit as a approaches infinity of the integral from 1 to a of, that's just x to the negative 2 dx. And then we can just integrate, right? So this would become the limit as a approaches infinity. Integral of x to the negative 2 is negative 1 over x, evaluated from 1 to a. So we'd end up with the limit as a approaches infinity of negative 1 over a minus negative 1 over 1. Plug in infinity here, that becomes 0 plus 1. So we just get an area of 1. If this comes out to be any sort of infinite value or any part of this limit doesn't exist, we'd say that the integral diverges and that there's an infinite amount of area underneath that curve. Just to briefly touch on the series stuff, also you can use these integrals if you have a series that looks like, it looks like 1 over x squared. So like if I had the series of 1 plus 1/4 plus 1/9 plus 1/16, infinitely long, we could rewrite it as an integral and use the integral test because we know that it's a series that has all positive terms and that is always decreasing. And if we did the integral test, we'd basically write this exact integral, say that integral converges to a value of 1 so that we know that the series itself of 1 over x squared or 1 over n squared from n equals 1 to infinity also converges. And we would know that converges also just by the p-series test. We proved it way back when. But just a quick side note there on improper integrals and being able to use them on the integral test. So improper integrals can go towards negative infinity or towards infinity. Could do negative infinity all the way to infinity. In that case, you would just need to separate it at some point in the middle and do 2 different limits. One is we approach negative infinity from, like let's say, what's a good function here? No, it's not going to work. Give this a second to think. Well, let's just do this. Let's just do the integral from negative infinity to infinity of 1 over x squared plus 1. I know that'll work out easily. So we can just split this in the middle. We'd say this is equal to the limit as a approaches negative infinity of the integral from a to 0, let's say, of 1 over x squared plus 1 dx, plus the limit as a approaches positive infinity of the integral from 0, or I won't say a, I'll say b, 0 to b of 1 over x squared plus 1 dx. And here we can just go through and integrate 1 over x squared plus 1 is inverse tangent x from a to 0. And the limit is b approaches infinity of inverse tangent x from 0 to b. And the inverse tangent of negative infinity is negative pi over 2. So we end up with 0 minus negative pi over 2 plus, then the inverse tangent of infinity is pi over 2 minus 0 again. So we'd end up with pi over 2 plus pi over 2, which is pi. So if you have infinite limits on both sides, you got to split. If you have an infinite limit in the middle, like if you have a vertical asymptote in the middle, then you've got to split it at that vertical asymptote, not split it at the vertical asymptote, but you've got to use that limit for that vertical asymptote. So if I was looking at something like the integral of 1 over x minus 2 let's just say from 2 to 3, we'd, since we know we have a vertical asymptote, our limit there at x equals 2, we'd rewrite this as a limit as x approaches 2 from the left, because our rest of our integral is to the right of 2, of the integral, not x approaches 2, but a approaches 2. So you have a to 3 of 1 over x minus 2 dx. And, we can finish solving this out if we want. It's going to come out to be divergent. It's from the left, Adrian, because this integral is from 2 to 3. Oh, sorry, from the right. From the right, because our integral is to the right of everything, and our thing is to the right of 2. That's my fault. Sorry. You're right. That should be 2 from the right. So the limit is a approaches 2 from the right of our integral from a to 3 of 1 over x minus 2, which is natural log absolute value x minus 2, evaluated from a to 3, which gives us natural log of 1 minus the natural log of 0, right? And we know that this does not exist, therefore this integral diverges. And we'll keep in mind also that if this was like 1 to 3, we'd have to split into 2 different integrals, one from 1 to 2 and the other from 2 to 3, and we'd have to do limits on both sides of the value of 2. I think that's pretty much everything with the integral stuff that we need to deal with. We didn't really get to talk about vectors at all, displacement and all that stuff, but we can touch on that before we do a little more review on series over the next couple of days. Any other questions on any of the integral stuff? I'm glad Zoom decided to hold up and not do whatever it was doing, so that's good news. Any questions or anything you think I left out from all the integral stuff? Yes, I can go back to the last one. Oh, there's a giant blue line through the middle of it. That's weird. Oh, I thought of one other thing we should just quickly mention. Let me know when you're good on that slide there, Nick. Or if you have a question on it. You're good? Okay. One other thing, this will just take half a second here. But anytime you're asked for the average value of a continuous function, anytime you're looking for the average value of a continuous function, remember that's 1 over b minus a times the integral from a to b. So you should know that, mean value theorem for integrals. Just wanted to quickly mention that also. Other than that, I think that's about it for integrals, for basic just integral stuff. Anybody think of anything else or any questions on it? We could talk about shells. Shells are not required. We don't really have time right this second, but just remember, if you want to use shells, you can. The formula for that is always the integral is 2 pi times the integral from a to b of the radius times the height times your thickness, which is dx or dy. So that's the formula. The radius should always just be, if you're going around the x-axis or the y-axis, the radius should always just be x or y, and height is usually like the difference between 2 functions which you might have. We can do a problem or so with that tomorrow if you guys want, but nothing on the AP test will ever require you to use shells. Just every once in a while, it might make it a little bit easier, where you don't have to convert the variables from x to y or something. But yeah, you won't have to use it.